Okay, good. So, welcome to today's class. So, here we are going to break the topic into three major components. Okay, of course, we are going to understand what is linear regression analysis. Okay, after that, we'll look at factors or some assumptions which we consider when doing what? When doing linear regression. Okay. We will as well create a model. All right. We'll create a model. And then after creating that model, we are going to, that is to measure. Okay. We are going to measure, that is how reliable our model is, or how good our model is. And of course, with this, we are going to use what we call, that is coefficient of determination. Okay, coefficient of determination as our major determinant. Okay, and of course we'll also look at different what different that is ways which we can that is determine the goodness of our model, or how our model will be reliable. Okay, and this will also discuss about the p-value. Okay, because we'll be trying to see if our model it is statistically significant, or it is statistically makes sense. Okay, so of course we are going to check on those components. So this is a topic which will take let's say at least three classes. Okay, extensive classes, three classes, maybe, and then on the fourth class we will do what we'll do practicals. Okay, all right, good. So let's start, and first of all define what we call that is linear regression. Okay. Okay, so for linear regression, analysis is used to predict the value of a variable based on another variable. So here we are discussing two variables. Even though at some time you might be having more than what? More than two variables. For simple linear regression, we are discussing of one predictor variable and one independent variable. Sorry, one dependent variable. Okay. When we are talking about multiple linear regression, we are talking about what? We are talking about one dependent variable, but more than one independent variable. Let me illustrate that. And I'm going to use a very simple that is equation, which it's somehow an example of what? Linear relationship. Okay. If someone can tell us what equation is this? Which equation is this? Someone? Yes, Alex?
Equation of a straight line.
Yes, it is the equation of our that is of a straight line. Okay, meaning it has a linear what? A linear relationship. That is y and x. Since we are talking about a linear, a line, they have what? They have linear relationship. So first thing, for linear regression, one of the assumption is that the two variables must have what? A linear relationship. If they don't have a linear relationship, then we cannot perform linear regression on what? On those two variables. Otherwise, we'll be forced to go and that is a look on that is for another independent variable. Okay, so in this case, y is what? Y is our dependent variable. Sorry, Y, it's our dependent variable, and X, we know it is our independent, so it is our independent. Okay, and then we have that is C. C, it's a constant, and M, it's a constant. But what is the name of this constant? Okay, we know that M, it is the what? It is the gradient or the slope. Okay, it is the slope or the gradient, or we can as well call it constant attached to what? To the independent variable. Okay, or that is a constant attached to x. Okay, then we have C, which is what? Our y-intercept. I'm going to illustrate that. Okay, it is our y-intercept. Okay, so basically this is an example of a linear equation. This is, in fact, this is a linear equation. Okay, equation of straight line, we know it is a linear equation. Okay, all right, let's assume if maybe we were given a data set. Okay, let's assume we were given a data set of this kind. Okay, we have some data points. Okay, we have some data points. Okay, and you are told to come up with what? With the equation of straight line. Okay, or you come up with the line of best fit. Let me assume this is my line of best fit. I don't know if I will draw it accurately. Let's assume this is what? It's our that is a line of best fit. Okay, so if this is our line of best fit, okay, and assume at this point, let me just extrapolate it. Okay, so in this case, let's say here it is 5, we have 10, we have let's say 15, we have up that is 20 as we continue. Okay, and then we also have, let's say, a 2, uh, 4, let's say we have 6, we have, let's say, 7, sorry, 8. Okay, basically I can't draw it perfect since I'm using the draw, so I'm just drawing. So let's assume we have our variable y and our variable x. Okay, we know that these are x y coordinates. These ones are x y coordinates. Okay, it's like at this point we have a specific um, that is value of x and a specific value of y. All right, good. So let's assume we want to that is find the equation of the straight line. I know in this case you did this in high school. Okay, so of course if we want this, we will only we'll only get two constants, that is m and what? And c, that is the the slope, okay, or gradient, and then the y-intercept. Okay, of course we know the y-intercept, it is the point where our equation line, okay, let's call it m. Okay, this linear or line, okay, straight line, where it cuts the y-axis, it's that point, it's what we call the y-intercept. Like for example, if we extrapolate our line, okay, So let's assume it cuts that is the point at what? At 4. Okay, we will know that then our new equation, that is uh, equation of straight line, will be that is mx plus 4, because it is on the positive side. Okay, if it was on negative side, then it could be on this, that is below the what? Below the x-axis. So in this case, we will have what? Negative y. Okay, so this value, it's always plus or negative. It can be a negative value or a positive value. Okay, then of course you can as well calculate your slope. Okay, you can calculate your slope. Let's assume you want to measure, that is this point, okay, and this point. You can do what? You can that is just do a right angle, that is a triangle between what? Between these two values. Of course, this will be change in y, and this will be what? Change in what? Change in x. Okay, we know that is slope is given by change in x, sorry, change in y, right? uh, just a minute, I want to remember it well. It is change in x over change in y, right? Sometimes it confuses me. It is change in x divided by change in y. Change in x divided by change in y. Okay, so meaning this value minus this value, you'll get change. Okay, change, we are looking at the difference between this value. Let me use a different color. Between this value, okay, basically it will be here, just a minute, it will be that is change in, okay, change in x will be this value here. Okay, let's call it x1 minus what? X2, this value. Okay, and then for change in y, it will be now this value. Let's assume we are talking of this value. It is y1, okay, minus y2. Okay, so this point, like if you take this point minus this point, so it will be, our slope will be x1 minus x2 divided by y1, or you can use either that is the largest minus the smallest. So y2 minus y1. Okay, so it will give what? It will give you the slope. I hope we are together. I hope we are together. Maybe by the show of thumbs up. Um, Silence has dominated. Okay, so good if we are together. So in this case, you'll get what? You'll get your slope. This is just a mathematical computation of these, that is these values. But we are going, when we'll be doing our practicals, we won't need to do what? We won't need to go through this procedure. So I was just explaining, that is the formula behind, what we are doing, what the formula behind what you are discussing. Okay, all right. Good. So with that, we will have now the value of what? We'll have the value of our m, and of course we have the value of what? Of our y-intercept. So in this case, you will have a complete what? A complete model, or a complete equation of line. Okay? Equation of straight line. Okay? So when we will use our, that is our rainfall, we will use our rainfall and umbrella cells data for this practical. Okay, as well you can do your practice using the monthly, okay, using the monthly income and the monthly expense, of course, to do what? Expense to of course practice, right? Yeah, so I will use rainfall amount and the umbrella cells, okay, on that topic. Good. Any question before I can now start the that is the the theory part of it? I guess you've understood this concept. Okay. This concept, also equation of straight line concept, can be used to do what? To build a salary. Okay. Let's say a salary model. Given maybe we want what? Experience. Like we are only using experience as the key or as the main factor that influences what? Salary. Okay, so you can do what? You can come up with a constant, let's call it a, multiply by that is work experience. Okay, work experience, then plus what? Plus or minus a constant. Okay, so you can see this is a model already, which we can create. Okay, so meaning we will use work experience in years, okay, to determine what? To determine the salary. The salary may be which you need to do what? Which you we maybe we will pay for a specific role. Okay, so basically what in this case we'll need the data for monthly salary and the data for the what? For the that is experience. Like if this person is paid 40,000, what is his experience? This person is paid 70,000, what is his work experience? This person is paid 100,000, what is in its experience for the same role? Okay, so basically that's something we will need to do what? We'll need that is to consider. All right, okay, good. So back to the notes so that we may develop or build our basis when it comes to what? To linear regression. Okay, all right. So what is linear regression? So linear regression analysis is used to predict the value, okay, of a variable based on the value of another variable. The variable you want to predict is called dependent variable. Like for our case here, we've said why, let's say the umbrella, okay, umbrella cells, okay, all the umbrella sold uh, equal to a constant. Let's say constant, it's a, of course it's a bit raw, okay, a multiply by rainfall amount, rainfall rainfall amount rainfall amount, okay, plus or minus what? Another constant, let's call it b. So this will be our model. Okay, and in this case you can see it is taking the what? The same format of equation of what? Straight line. Okay, we have a constant attached to x. You can see a constant attached to our independent variable, and then we have a constant which is the y-intercept. Okay, so in this case, y, we are saying it, we are trying to predict y is the outcome, x is the input. in simple language. Okay, so we are trying to get the outcome, or we are trying to predict the outcome. Okay, so the outcome will be what? Will be our dependent variable. Dependent variable in comparison to what? To our input. Now, in this case, our input will be our independent variable. We can say y depends on these values. Okay, all right. So y depends on these values, or y depends on this variable, but this variable, it is independent. Okay, so we call y the dependent variable, we call x the predictor variable, or the independent variable. Okay, sometimes known as explanatory variable. Okay, as it explains more about what? About our output. Okay, all right. So let's continue. Just that was just an illustration. So you, the value you want to predict is called the dependent variable. The variable you are using to predict the other variables value is called independent variable. So in this case, x is our independent variable and y it's our dependent variable. This form of analysis estimates the coefficients of the linear equation involving one or more independent variable that best predict the value of what? Of the dependent variable. Okay? Linear regression fits a straight line or a surface that minimizes the discrepancies between the predicted variable and the actual values. Okay, so of course, if we have a very minimal distance between the predicted and the actual values, then we usually say that model is strong. You'll come to find that the standard error in that case, it's minimum, or what we call the error term, it's very small. Okay, so the stronger the what, the better your model. Okay, we shall look at those factors, don't worry. So linear regression fits that is a straight line, um, or surface that minimizes the discrepancies between the predicted and the actual output. There are simple linear regression calculators that use least square methods to discover the best fit line for a set of what? Paired data. I know you used least squared method, least squares methods back in Canvas for those who did statistics. Okay, where you were calculating that is the values or you were creating a linear model using all those computations. Okay, all right, good. So let's continue. Linear regression performs the task to predict a dependent variable value y based on what? On a given independent variable x. So you can see in this case, like we are predicting the y using values of what? X. That's why we are saying linear equation performs the task to predict a dependent variable value y based on a given independent variable x. So this regression technique finds out a linear relationship between x, which are the inputs, and y, which are the output. Hence the name is linear relationship, because they are trying to come up with what? To come up with a linear relationship between what? Between those two variables. Okay, that's why we are even calling it linear what? Linear regression. All right, that's why we are calling it linear regression. Good. So in the figure above, okay, you can see that it is what? Let me check. The figure above, that is the x inputs, is the work experience in years, and y output is the salary of what? Of a person. The regression line is the best fit line for our what? For our model. Okay, and you can see the data points are scattered close to the what? Are scattered to close to the regression line. Okay, this straight line is known as regression line. Okay, so you can see the data points are scattered. These are people's salaries. Okay, depending with what? With the years of the experience. Okay, so if they are close to the that is the regression line. Okay, then it means that the model which you are going to get here, it is what? Will be very strong. Okay, will be very strong. And like maybe let's assume we have that is a linear equation which that is a regression line which looks like this. You can see like our data points, like you can see we have I outliers within our what? Our data sets. Okay, like an outlier. You can see this person here is paid high salary amount. Okay, but as what? Very few years of experience. All right, then you can as well look at this. You can see this person has worked for, has a very that is has many years of experience, but the salary is very minimum. Okay, so with this kind of data, then we cannot come up with what? With a strong that is model. Okay, we cannot come up with a strong predictive model or salary predictive model. Okay, all right, good. So that's why I'm trying to show you that is the difference between the first illustration, and let's assume maybe when your data points are along or close to what? Close to your regression line. Of course, in this case, you'll come to get that is a model which is very strong. Okay, even the correlation will be strong here, and here the correlation will not be what? Will not be strong. All right. Yes, so those are just some aspects you need to understand when it comes to linear regression. Okay, so then of course we have the hypothesis function for linear regression. This is it's this one. So we say that we have the intercept, that is the y-intercept, and also we have the coefficient of what? Of x, or coefficient attached to x. Okay, good. Let's come to types of linear regression. Of course, I had introduced this. Okay, I had introduced this already. So when it comes to types of linear regression, we have multiple linear regression and simple linear regression. Okay, for simple linear regression basically involves one independent variable, okay, and one dependent variable. But majorly here, we are focusing about what? The independent variable. Here we will only have one independent variable. But for multiple, as the term says, multiple meaning many. Okay, so for multiple linear regression here, it will involve more than one independent variable. Like for example, let's assume we have an equation that is a simple linear regression equation. Okay, will look like this. Let's say y is equals to m, or let me just use another variable, will be like ax, okay, plus let's say b. This is simple linear regression equation. Okay, but for multiple linear regression, okay, MLR, okay, equation, will be equal, that is our dependent variable will always be 1. Okay, but we'll have different what? Different independent variables. So we can say that we have that is our constant, our first constant, that is our with our first variable, plus let's say b, and our second variable, let's say x1, then plus what? Plus c. And sometimes let me write this well, plus c. Sometimes we can add what? We can add what we call epsilon. Okay. Epsilon, basically it's the vertical deviation, or what we call the residuals. Okay. Let me just show you. So like when I talk about epsilon, I'm trying to measure the distance between this point and the regression line. Okay. Not this, not this, not this, not this, but it's a vertical deviation. We are talking of vertical deviation. All right. The all the residuals, it is known as the error term, the residual, the and as well as the epsilon. Okay, or the y deviation. So this is what this, it's basically measures the distance between a data point to the what? To the the linear regression line. Okay, yeah, so that is the distance. So that's why I have added what? An error term in what? In my equation. All right. All right. Are we together up to that point? How many we are together? How many have floated? So Abed, Felix, Timothy, I can see most of you are okay, but still those are less than half of the class. What about the others? Okay. So for multiple linear regression, I can start, and I will give you now an illustration. Give me some factors which affect or which bring high blood. That is it blood pressure? High blood pressure. Someone? Do you have someone from medics? What are some of factors which contribute to high blood pressure? We have obesity, yes. Another one,
Smoking.
smoking. Let's go with those two factors, right? Those are two factors. Good. So these two factors are our independent variables. Why? For they influence, they do influence what? The blood pressure. Okay. So, like for example, we can take maybe the readings of obesity. Basically, shows it's the weight ratio. Okay, is it the body mass what with weight ratio? I don't know the computation which happens beside that. So, our blood pressure, we are trying to predict maybe if someone has a blood pressure. Okay, and we have values for or we can predict if the like how does blood pressure sorry, how does obesity contribute to high blood pressure, and how smoking can contribute to high blood pressure. So in this case we are predicting the high blood pressure values given values of smoking data and obesity data. Okay, so in this case, we are going to say our first constant, okay, multiply by then obesity. Like obesity is our first variable. So I'm going to write obese. Let me just write this one in brackets, meaning it's what? It's multiplication, okay, plus our second constant, okay. Then we have what? Smoking data, okay. Then plus our constant, that is the y-intercept. So in this case, you can see we are having what? Two variables. These two variables influence our outcome here. Okay. So in this case, we can given maybe a data set on obesity and data set on smoking, that is smoking. Then we can do what? We can predict maybe the what? The blood, the high blood pressure level. Okay. So basically these are two factors. Okay. All two independent variables. That is independent variable 1 and independent variable 2. Okay. Of course, someone else can try and narrow down, and I want to decide. I want to see how smoking contributes to what. Like if I want to have a visibility, because let's assume if these two variables are highly correlated, if obesity and smoking are correlated, okay, then it will be hard to us it will be hard to for us to know which factor contributes, that is greatly to high blood pressure. Okay, so we'll come to see on that assumption, that is these two variables should not, or should have minimal what? Minimal correlation. Okay. Yes, there should be no multicollinearity. Okay, we'll check on that when it comes to the assumptions. Now, I might decide to narrow down, okay, my that is my study to what? To smoking only. Okay, to smoking, meaning I have data for smoking, or let's say obesity will make better sense, maybe, or obesity, and see how obesity has contributed to what? To high blood pressure. So in this case, you can see we are only factoring what? One variable, that is obesity, but for the first scenario, we are using more than what? More than one variable. You can see we are using two independent variables to determine what? Our output. So that's the difference. Multiple linear regression that is involves two factors, okay, to determine your outcome. But for simple linear regression, uses only one factor to determine your output. Is that now clear, Joroge? Nice. All right. So let's continue with our notes. So of course, all this illustration was just to summarize this. So for simple linear regression, if a single independent variable is used to predict the value of a numerical dependent variable, then such a linear regression algorithm is what? Is called simple linear regression. Okay. Multiple linear regression, if more than one independent variable is used to predict the value of numerical dependent variable, then such a linear regression algorithm is what? Is called multiple linear regression. Okay, you can see one we are using that is we are using more than one independent variable, and the other one we are only using single, that is independent variable. Okay, I hope we are clear up to that point, and I'm not going with high speed, right? I hope the speed is okay. Good. Let's now go to linear regression. Okay, Linear regression can be of two types. Linear regression can be of two types. It can be a positive linear regression and it can be also a negative linear regression. What do I mean? Okay, so let's assume you have two factors, okay, and let's say y and x, okay, and as one factor is increasing, the other factor is what? Is as well increasing, okay. Like for example, this is a positive, this is a positive what? This is a positive regression. This is positive regression. Why? Let's start with the first value of y. This is y1, okay, and this is what? X1, okay. Let's go to this point, other point. So this one is x2 and this one is y2, okay. If we go to the other point, the third point, okay, so this is y3 and here we are having y3, that is, sorry, x3. So what can you see? You can see here the values are what? Are increasing with increase in what? In our y values. Like as the y values are increasing, so does the x values. Meaning they are moving in the same direction. They are increasing all together. Okay. So you can see as this one is increasing, okay. You remember here we have 1, let's say 2, and we have 3. Here we have, let's say 1, 2, and 3. As we move from 1 to 2, it is a one step increase. If we go from 2 to 3, it's a increase. If we go to y1 to y2, it's an increase. So that's why we are talking about that is a positive increase, okay, or a positive regression. What about a negative regression? Okay, so in this case, as one variable is increasing, the other variable will what? Will decrease. Okay, the other variable will decrease. And for a negative regression, that is line, it always looks like this. Always looks like this. This, this is negative regression line. Okay, why? Because let's assume we have this value of, let's say it is y1 and this is y2 and this is y3. Okay, we have this one, it is, let's say it's x1, this one it is x2. So basically you can see, as you can see, at the highest point, okay, at the highest point of y, we are having the lowest value of x, okay. At the lowest value, sorry, at the highest value, okay, of x, this is, remember, if we are saying this is 1, of course the scale will go this way and here will go this way. Let's say in this case we can say 1 will be declining, okay. Like if 1 is declining, the other one is increasing. Like for example, at the highest point of x, okay, value of x, you can see we are having what? A corresponding low value of y, okay. Like as one variable is increasing, all right, the other variable is what? Is decreasing. Like for example, if we are to extrapolate this value to this point, okay, you will find that the value of y will continue to do what? To decline, okay. Like one variable is increasing while the other variable is what? Is declining. So this becomes the negative value and this one because it becomes what? A positive regression value. All right. Okay, good. Let's continue. Now on the notes, we have linear regression line. So a linear line showing the relationship between the dependent and the independent variables is called regression line. A regression line can show two types of relationship: a positive relationship and a negative relationship. Okay, a positive relationship, okay, will show us that is if the dependent variable increases on the y-axis and the independent variable increases in the x-axis, then such a relationship is termed as a positive linear regression. Okay, so so positive linear regression, okay, if the dependent variable, you can see the y in on the y-axis is increasing, so does the independent variable in the what? In the x-axis. Okay, so you can see they are what? They are both increasing. Okay, then for negative linear relationship, you can see if the dependent variable is decreasing on the y-axis, then independent variable is increasing on the what? On the x-axis. Like one variable is decreasing as the other variable is what? Is increasing. Okay, so in that in such case, we talk about what? We talk about negative linear relationship. Okay, we'll talk about negative linear relationship. Is that clear? I hope that point is clear. Good. Let's continue. So finding the best fit. Okay, finding the best fit. So in this case, we are talking about that is how can we optimize? Okay, how can we optimize? And optimizing basically here means like we are trying to find the best values of our coefficients, okay, so that we may optimize our, that is our model. Okay, it is called model optimization. So we have some functions, like we have some methods of what? Of that is of let's say model optimization. Okay, so finding the best fit line. So when working with a linear regression, our main goal is to find the best fit line. That means the error between the predicted values and the actual values is very minimal. Okay, so the best fit line will have the least error, or it will have the least error term. Okay, so that is one method of what? One method of defining or one method of checking if your model it's what? It's okay. All right. So in this case, whenever you are having a very small that is error term or standard error, you'll what? You'll find that your what? Your model it's very good. Okay. However, the different values of weights or coefficients gives a different regression line, that is different line of regression. So we need to calculate the best values of a0 and a1. That is basically, these are our coefficients, the gradient and the y concept. So for us to come up with for us to optimize or to get a better regression line, we have to optimize our what? Our weights or our coefficients. And how do we do that? We usually use that is a method which is known as cost function. Okay, I want us to to discuss on cost function, and then we will end it at that point. Okay, so that maybe tomorrow we might discuss on the model performance, and then the assumptions. Okay, and then after the assumptions we'll try to do what, we'll try to do some that is some um, practicals. Okay, so after that we'll do some practicals. What will take time is now explaining our output. Okay, what will take our time is to that is understanding our output. Of course, running regression will use three major methods. We have three major methods. That is that is using a linear graph and a trend line. We'll also use what we call, of course, the analysis tool pack, and we will as well use what we call, we will as well use Excel, the inbuilt Excel. So we are going to perform that is linear regression using three different methods, but getting the same what, the same results, and we'll look at that. Okay, so basically cost function, we only have one cost function which is commonly used, and that one cost function is known as the mean squared error. Okay, so the more that is the more we minimize the mean square error, okay, which is our cost function, okay, the stronger our coefficients. And if our coefficients are okay, then we will have what, we'll have a better regression line. So cost function, we have the different values of weights or coefficients. A one that is a 0 and a 1 gives different line of regression, and the cost function is used to estimate the value of the coefficient for the best fit line. Sorry. Cost function optimizes the regression coefficients or weights. So in this case, cost function method will only optimize what? Will only optimize the weights of our regression equation. Okay? It won't optimize anything else, but it will only optimize what? The that is the regression coefficients, meaning we are trying to get the best, okay, the best that is coefficient. This can be as well be done through trial and error, okay, to see at what point or at what values of coefficients will we get what, will we get the smallest cost function or the smallest value of mean squared error. Okay, so cost function optimizes the regression coefficients or weights. It measures how a linear regression model is performing. We can use the cost function to find the accuracy of the mapping function. Okay, of course, the mapping function, it's more of the hypothesis that is a function. Okay, like the function, you can go and check on the mapping function. You can just go and Google on basically what is this mapping function, and you will see what it is. Okay, so for linear regression, we use mean squared error cost function. So this is one of our cost function, most commonly cost function when it comes to linear regression, which is the average of the squared error occurred between the predicted values and the actual values, and it is given by this formula. I know you've maybe those who did statistics have ever came across this formula. Okay, that is the mean squared error is given by summation of yi's are the what, yi's are the actual values. Okay, then we have the y-hat. If you can remember, let me try and see if I can remember. We said that the mean that is squared error, okay, is given by summation of xi's minus y-hat. Y-hat, we are calling them that is predicted values. Then divide by what? Divide by n. If it is 4, I guess divide by n. I don't know if in this case it will apply. That is the knowledge of if it is a sample data or if it's a population data. But what I know, it is that is the squared. Of course, we will square this. If I am not wrong, we will have to square that because it is mean squared error. Okay, we'll have to square that. So basically, this is what? This is the formula for mean squared error. Okay, we know that y-hat is what? It's same as now putting all your values in what? In a model to predict that model. Okay, to predict that model. And you can see this can be what? This. So whatever they have done here, they have just taken the summation of yi's, okay, then they have minused the what? The that is the predicted, which is the y-hat, okay, a plus bx, okay, then you square and then divide by what? Divide by n. So basically, this is the formula for mean squared error. Okay. What I can conclude here is that the smaller the value of mean squared error, the better our coefficients are. And that's how cost function works. If we try to minimize the value, meaning these values we are bringing it to zero, to close to zero at minimal point, okay, then it will mean that we'll have a better that is coefficient values, okay. And if we have good coefficient values, then we'll what? We'll have that is we will have a strong model, okay. We'll have a strong model. Good. So basically, this is the formula. So n is the total number of observations, yi is the actual values, and this one will be what? Our predicted value. Okay. Then the residual. Okay, that is the difference. So the distance between the actual and the predicted value is called residual. If the observed points are far from the regression line, then the residual will be what? Will be I, as I illustrated in this example, where I showed you example of when we have values far away from the regression line and when we have values close to the regression line. So in this case, we expect to have a very large value of what? That is mean squared error, okay. And here this will be high value and this one will be low value. And when it comes now to prediction or using your model to predict, then this will be more accurate compared to what? To this one, okay, compared to this one. All right. But I know, of course, we'll understand better, okay, we'll understand better that is on this topic as we will be doing our practicals, okay. You'll see the values which we are going to get. We'll use two different that is data sets, okay, and you'll see the deviation which we will have, okay. You'll see the deviation which we will have. So if the scatter points are close to the regression line, then the residual will be what? Will be small. Hence, the cost function will as well be what? Will be small. And our values, that is our our model will be more strong. All right. All right. Otherwise, that's all on today's class. I do welcome questions.